Hi, I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. This video is overviewing Chapter 3 in Tinoco's book, Physical Chemistry, Principles and Applications of the Biological Sciences. Specifically, Chapter 3 is covering the second law of thermodynamics, or what I'd like to say is the first part of this chapter is introducing entropy. Now, entropy is what I would say is probably the most critical and key concept that we get across in thermodynamics and is used in all areas of chemistry, biochemistry, physics to understand the macroscopic world. And it's a critical aspect in how we understand heat, how we make reference to the microscopic world, how we even understand kind of time through the arrow of time as the increase in entropy. And what I would say is that this topic can be approached from lots of different angles, and you'll see it in numerous stages in your chemistry and physics fundamental work. So besides what the introduction you've already been given in introductory chemistry and physics courses, we're covering it again in this chapter in Tinoco's book. It's covered the same way in Jim Allen's book on biophysical chemistry. But this is one where I would say, as I've stated before, numerous resources often really help. If somebody asks me, one of the key concepts I use in trying to really understand a topic, a fundamental topic in chemistry or biochemistry, it's often really gathering multiple resources, which is often what you're doing in a class as well. You're listening to my video as well as reading the book, as well as looking up things online on Google and Wikipedia, etc. So not to belabor the point, but just to remind us of several resources. One is the one you already do. Whatever a book I assign, like Tinoco, is something you probably will look at. But it's really critical to realize that this was one book. There are lots of books on this topic, both books on just thermodynamics or books in physical chemistry, lots of different textbooks in physical chemistry, even ones specifically for the life sciences or biological sciences. And it's really often useful to find the chapter associated with the second law and introducing entropy and look at some additional books. And this is where I would say, your library is a very useful resource. So the ASU library, both online versions as well as hard copies of the text. As you all already use online material, both ebooks, but also just websites that have this information like Wikipedia, etc. The one that I would say students rarely use that I consider really useful, and I would strongly encourage students to look into adding to your resource list, is really journal articles, review articles, peer-reviewed manuscripts, annual review in different topics. There's annual reviews in physical chemistry that often are books that have chapters on this, etc. But there are lots of good review articles and peer-reviewed journal articles that will keep you up to date on a lot of the modern aspects in the research going into things like entropy. And then finally, what we're doing here, not only my videos, but there are videos from numerous other professors at both ASU as well as universities around the world on this topic at common places like YouTube, as well as things like EDX and MIT's online courseware, etc. And you'll find lots of videos and screencasts, etc. Some of my favorite additional resources I added, a site I upkeep, biopchem.education, where I have a whole list of various books and articles that can be used to get different perspectives on this same topic. So with that said, let's delve into how Tinoco introduces the second law of thermodynamics and entropy. And he does this by a very common method of looking at what we already have a familiarity with kind of gas laws and how pressure volume behavior of ideal gases. And so this is specifically looking at the Carnot cycle. And this cycle is, as shown here, where you start at some pressure volume of a gas, and then you isothermally expand it to a certain point. That'll be step one. Then you adiabatically expand it to here. So now that we've expanded it in two different steps, and we've already introduced two different kind of constraints on the system. The first is that we keep it at constant temperature, isothermal. The second is that we don't allow heat exchange. So here, this is isothermal as it expands, but then we're gonna change the container so that it's isolated so that we don't allow heat in and out of the system. And that's gonna be this adiabatic expansion, or no change in heat across here. Now we're going to move from the expanding stage to the compressing stage, and we're going to compress both in the reverse order, first isothermally at this colder temperature, and then finally adiabatically to end up back where we started. So, and this is what we mean by it being a cycle. We start and end at the exact same point that we'll say is pressure 1, volume 1 here. And so we look at this, and we can say the first thing is that we know at step under path 2 and 4 that the heat is 0. That's by definition that it's adiabatic. But we can look at the work in heat terms that will be along these two isothermal steps as well. And you'll see that here we have a positive heat. So basically heat is going into the system and heat is coming out of the system in step 3 when we're doing this isothermal compression. And you'll see that the work is opposite of that, is the opposite sign of that. And we know one thing, we know that the internal energy is a state variable. And so the overall change in internal energy of this complete process must equal 0, right? Because if we start and end at the same place, we should be at the same energy. And so this is just, your book goes through this process using kind of an ideal gas equation of state, which makes it easy to do the derivatives and integrals, to be able to follow the exact process of this and look at this cycle. And so when you do that, you'll see, we know since there's no change in internal energy, that the change in the work must be equal and opposite to the change in the heat associated with the system, right? And when we do this, in a sense, go through these 4 processes, add them all together, or in a sense integrate this, so like it ends up being this area that we end up looking at, right? And so we can look at that step by step, and this is what your book does, for an ideal gas. And one of the key concepts that's really born out of this is that if you look at the, how the heat, you changes at each one of these at step 2, 3, and 4, you add all these heat up together, right? You realize that, that overall this cycle, it's path dependent, that the sum of all the heats, isn't a conserved quantity or isn't 0, but it will be equal and opposite to the change in the work, which will make this overall state variable. But we notice that if you, instead of just looking at the how the heat changes, but if you normalize it by the temperature, that does in this cycle, if you keep it, a reversible cycle where you do this slowly with an ideal gas, etc., that this does end up being conserved quantity. And this is one of the key findings of Carnot, is looking at these cycles, and that's what this integral with a circle around it is meant to indicate, that it's along a cyclic path here. This is showing it in the original pressure volume space, and this is showing it in this new variable that we're going to equate to this normalized heat. Specifically where we mentioned that it's following a reversible path. So looking at step 1, we keep it isothermal, but what we are changing, in a sense, is the heat. We're bringing heat into the system, or entropy, right? And this is what we're going to define as this new variable. This is really the fundamental of the second law, is defining what heat is as far as the change in heat is temperature times the change in entropy. And it's equal to that for a reversible process. Now, one thing that ends up being an immediate confusion for students is that this is really an inequality, and it's talking about when you do things in random ways where it can be irreversible in processes, often that gets split up into kind of its reversible part and its irreversible part. And for this part of thermodynamics, we generally introduce it as it can be for any process, any reversible or irreversible process, but we quickly in the book just limit ourselves to talking about reversible thermodynamic equilibrium processes. And so you're going to quickly see us go from an inequality to the equality where you're always following a reversible path. So, and then this is undergoing this adiabatic, which is really now we can see it's defined as no change in heat, but that's going to equate to no change in entropy along this path. And now, again, we do the compression state isothermally and then back up to this state here. So this is showing it in temperature entropy space. And these two areas are equal to each other because you're coming back to the same energy point in this system. And so what I like to write as a general expression for the second law is that the change in entropy is greater than or equal to, and whether it's a capital Q or a small q, so I would say these two are equivalent to each other. These get interchanged a lot in different texts and different versions of writing it, but they're really meant to write the same thing. And the most critical point here is that what we're often saying is where it's equal to is when you're looking at reversible processes. And this is really what we're going to be doing in this course, which is looking at reversible thermodynamics. And there's lots of different statements of this. The entropy of the universe tends to increase or maximize. The total entropy of an isolated system, so again, one where you completely shut it off, where there's no change in the number of moles, but there's also no change in heat of the system, can never decrease over time. So if it's isolated and everything that's happening is reversible, then it'll be, the change in entropy will be equal to 0, or the change in heat. But it can only go one way, which is it can only increase, it can only be greater than 0 if something irreversible is happening in these isolated systems. So, and this brings up another one, as I mentioned at the start of this video, besides resources in looking this up like Wikipedia, I also strongly advise Everpedia, which is sponsored by Wikipedia on a blockchain and is edited content to make sure a lot of it is very clear. A lot of it is just regurgitated Wikipedia, but one that has been really edited for accuracy, etc. So, and this is where a lot of this is covered in very good detail online about the second law. Another way of generally stating this that relates to the last one is if we look at it, over a cycle, how this changes over a cycle, it's always, so if we flip this around, that flips the sign, so less than or equal to 0, right? And if this is reversible, where this is specifically a reversible path, then this is equal to 0. And so this is often known as the Clausius inequality here. And this is the special case for reversible processes. And so this really gives us our most general aspect for the second law. It defines an arrow of time because it defines an arrow in which time increases as the entropy of the universe, if we think of the universe as an isolated system, increases. So there's a lot of implications to the second law of thermodynamics. But really we want to start practically using it in biochemistry. So I leave you with, like I said, that you can look up a lot of the references, and I strongly urge you to look up entropy. It takes a while to really get a sense for this, and there's really several different ways to look at it. Your book introduces it from what I would say like introducing it from the macroscopic heat perspective, or what I would call engineering perspective. Your book then also looks at it from a molecular standpoint. And we're going to soon introduce this, but looking at entropy as it's associated to the number of configurations of a molecular space. So we can look at it, and this was done by Boltzmann. But it can also be looked at in terms of its amount of information or information theory. This was pioneered by Claude Shannon in the 50s, basically. So you can also look at it kind of from an information or computational aspect as well. And all of these can be really, really useful to get a really good different perspective, fundamental feel for entropy and the implications of the second law of thermodynamics, or the second law we use to describe macroscopic systems. When we start looking at macroscopic biological systems, one of the first things we want to do is we've equated this to, in a sense, if we say that ds is equal to dq reversible over t, so that dq reversible is tds. So this is often what we think of. Now we're in reversible thermodynamics, the change in heat that we use it for our fundamental conservation of energy, or the first law. Now we can substitute in a temperature entropy term, right? But one of the first things, because this is really, it scales by the temperature. It's temperature times the change in entropy. So looking how the entropy changes with temperature, or the temperature dependence of entropy, it's one of the first things your book looks at. You can look at its pressure volume dependence. You can look at its different work function, how it scales with the number of moles, etc. So entropy is a state function. So like the internal energy. So, and that's what Carnot showed, that this Q over T ends up being a state variable. So, so we often look at it, instead of just looking at the heat, we almost always look at the entropy of the system. So let's look at its temperature dependence, and I'm first going to just, because what we want to do is integrate this, but we want to integrate with respect to a variable. So this will be, if we integrate this, will be the change in entropy. We want to integrate this, right? But we need to know how the temperature, or how the heat changes with temperature. So to get this into a differentiating where it's how it changes with temperature. Now dq dt is defined to be the heat capacity, right? And right now, if we're looking at the internal energy, it's dq plus w. So the combined first, second law is TdS, and we'll do pressure volume work here. So let's initially, we have to decide what variable we're keeping constant. We use C for the heat capacity, and then whatever variable is constant we put down here. So the natural one that implies to internal energy would be keeping volume constant, so that the internal energy is just the heat term, right? So if we do that, then it would be dq dt at constant V, right, over T dt, and now we can integrate that, right? So we can see how this changes. Again, if let's assume the initial assumption is that the heat capacity is constant with temperature, but you can put its temperature dependence. And then what's the integral of 1 on T, where 1 on T, where it's constant, where it's positive, will be ln T, right? So we'll see that how the change in entropy changes with temperature goes as a heat capacity times the natural log of the temperature. So where we'll go over some temperature range, and it'll be logs will go, it'll be T2 minus T1 or T2 over T1. Okay. And so we can look at this heat capacity. We could also look at it at constant pressure, which is more common to look at, and your book does that as well. So we can look at how these heat capacities change with temperature and make the temperature dependence of that here when we integrate out as well. So to remind us, when we looked at enthalpy, it goes as Cp dt. So entropy goes as or the heat, it will go as Cp on T dt. So it goes as, again, scaled over the temperature that you'll be integrating to get deltas. Now the third law doesn't get talked about in very much detail because it really just scales entropy. It gives us a scaling point that at absolute zero, or in the limit as temperature goes to absolute zero, entropy goes to zero. Or a better way of stating it is the entropy goes to zero as you approach absolute zero in temperature of the system. So this heat capacity, whatever it is, no matter what it's dependent on, this one would be the constant volume or constant pressure, goes to zero as you start reaching absolute zero. You can never reach absolute zero, but in the limit as you approach that, the entropy goes to zero as well. So it allows us to define kind of the absolute, the entropy at 0 Kelvin as basically approaching zero itself. And as we just saw, the integral of Cp on T, this area over, gives us the overall, how the entropy changes with temperature here. So after your book introduces it from what I would say a classical thermodynamic case, and I strongly urge you to now be able to do just this, take these ideal gases, undergo the isothermal adiabatic expansion, the isothermal adiabatic compression with an ideal gas equation of state. You can even define pressures, temperatures, volumes, etc. See these processes, work them out yourself. Maybe work a different equation of state, like a hard sphere equation of state or van der Waals equation of state as well, to really go through the Carnot process and make sure you understand it from this perspective. One of the critical aspects, and one of the reasons we come back and look at thermodynamics that we've already been introduced to it in kind of the introductory chemistry and physics courses for biochemistry, is to really look at it from a molecular standpoint as well. And this was really pioneered by Boltzmann, who realized that the entropy is a constant, which we now call the Boltzmann constant, times the natural log of number of configurations. And this is a little vague, but these configurations are the number of microscopic. So this gives us a realm into the molecular or microscopic world with this system. It also really helps us from a molecular standpoint, help us define what we mean by things going in a general direction with entropy. And we all have a general sense for this, and your book points this out, which is, for example, if we have on one side of this a high pressure material or gas on one side, and then we have a lower pressure gas on the other side, and we open that valve, we have a very good sense for what's going to happen here. It's going to equilibrate pressure. Specifically, this side is going to get a little higher in pressure and this side a little lower, right? So we know that, and it's never going to be the opposite. It's never going to be that the gas from here is going to flow directly into here to make this even higher in pressure and this even lower, right? We know that in equilibrating, by maximizing the entropy, this is going to equilibrate the pressures in this system. So we have a sense, if we have two gases on either side and we open the valve, we know that these two gases are going to mix together. We know that it's not going to be that none of the H2 gas is going to go to this side, and you're going to get all the N2 and O2 gas on this side and nothing on this side at all, right? We know that if you open these, what's going to happen is the mixture of the gases. We know that when we equalize, if we take a pressure cylinder right here and open it in the it's going to disperse across the room. It's not going to happen the other way where all the air molecules in the room are going to go into that container when we open it. So we have a sense that things are going to randomize or spread out to as many different configurations, in this case occupying as much of the volume as possible in a system. So when it's given the chance to occupy more volume, it spreads out evenly as it can. And so this is your book's way of starting to introduce this idea that it maximizes the number of microscopic configurations or where the gas goes. And you can really get a much better quantitative sense for this by applying the kinetic theory of gas that you learned in introductory chemistry and physics that gives you kind of a microscopic translational diffusion of these gases and translational speeds of these and apply it to these type of systems. Now, after your book kind of gives you some general introduction into both the molecular aspects of entropy as well as, like I said, kind of the basic thermodynamic engineering perspectives, the second half of the chapter then introduces a new type of energy that is used commonly in chemistry and biochemistry, which is the Gibbs free energy. So to remind us, we said that the internal energy of the system is path-dependent work and heat. And now we have terms for this. We know that in reversible, this is TdS, and we generally look at this introducing initially as pressure volume, even though we know we can have other types of work. We can have chemical work or the change in the composition, mu-dN, we could have electrical, magnetic work, et cetera. But we often limit our discussion to looking at kind of mechanical work here. And we've already introduced a different type of energy, one that we looked at when we looked at constant pressure systems. And we looked at this as the enthalpy. We said it was a Legendre transform, and we'll go through some more of the mathematics of that later, but that the enthalpy is defined to be U plus PV. And what that has, it basically flips these variables and flips the sign. So this is TdS plus VdP. So now instead of the internal energy being dependent on entropy and volume, the enthalpy is dependent on entropy and pressure. Now the reason the Gibbs free energy gets so important is that the Gibbs free energy is dependent on temperature and pressure. And then if we added later on, which is the most important reason, is we often want to look at the change in chemicals or number of moles of things, holding things at constant temperature and pressure. So just like we like to do things at constant pressure so that the enthalpy can be related just to the heat in the system, or the entropy now as we've seen, the reason we often use the Gibbs free energy instead of the internal energy is that we often don't want to, it's hard to hold entropy and volume constant, but it's much easier experimentally to hold temperature and pressure constant when we're looking at chemical reactions or how the chemical potential number of moles in something change. So this is by definition what it is. Therefore, since this is defined to be H, it can also be written as just H minus Ts, right? And like I said, the way we would write this is to flip both of these terms. So it's minus S dt plus V dP. And then like I said, you could have, the most common thing is to look at the change in the number of moles. So it's going to be the sum on mu I, the chemical potential, the change in the number of moles of each of those systems. So when we're initially looking at a closed system, this often term gets eliminated and we just write this right here. So that we see that the Gibbs free energy is dependent on temperature and pressure, unlike the internal energy, which is dependent on entropy and volume of the system. And so And this is often what we're looking at. And so we can look at it with respect to the inequality here, that while you're trying to maximize the entropy, you're often trying to minimize the energy. And so we look at minimums in the Gibbs free energy process. And as I wrote here, one of the most common things you see is the integration of this equation, right, which is that the change in Gibbs free energy is the change in enthalpy minus T, the change in entropy. And again, this is at constant temperature, so the S dt term goes away, which is what. And this is often in your book, especially in the biological sciences, is looking at the interplay between how the enthalpy and the entropy, changes in different types of biological processes is often what we look at. The interplay of the enthalpy of different bonding and intramolecular forces versus the entropy of maximizing the number of configurations available. And it's often the interplay of these two that we use to try to, at a kind of a microscopic level, understand, minimizing this Gibbs free energy and looking at things where when dg is 0 that you get spontaneous processes or things. This kind of helps define what happens, that you're minimizing these energies and going to the lowest free energy state for a specific temperature and often specific constant pressure that you're looking at a lot of these things. And so in looking at this now, we want to, from a microscopic standpoint, kind of define what these different ways we can change the energy through the interactions. And we have one sense already through covalent interactions. And this has been covered a lot when we introduce chemistry in general. And so in your introductory chemistry classes, looking at the enthalpy through covalent bonds and breaking and reforming bonds was done not only in chapter 2 in Tinoco, but is a review from past chapters as well. But one of the critical aspects in biochemistry is non-covalent bonds or non-covalent reactions, that it's really not breaking any bonds, but it's really that molecules are coming together and interacting without forming direct covalent bonds, but having some energy minimum or some interaction energy associated with it. And your book spends the last part of the Gibbs free energy defining what some of those are from a molecular standpoint. And so it starts by introducing it just from what we're very familiar with ionic interactions. Things like sodium chloride, that sodium plus and chlorine minus, the Coulombic interaction between them. And then it goes on to look at further, and so it gives you the thing that, this ionic can be broken up into solution, and it's because now there's a dipole with water that can associate itself around these ions. And so these ion dipole interactions, it talks about some of the strength of those, and then it goes through that even if the molecule doesn't have a dipole itself, it can induce a dipole. So an ion can induce a dipole in what would otherwise be a neutral or charge symmetric state. And so through the polarizability or the squishiness of the electron, you can get dipole-induced ion or dipole-induced dipole interactions. And all of these kind of get thrown under van der Waals interactions, but understanding each of them, and that you can have induced dipoles that once it has an induced dipole, it has a forced induced dipole on another neutral molecule next to it, or London forces. And then a specific type of bonding that we call hydrogen bonding, which is really a three-centered type bond that gets introduced a lot when we go into inorganic chemistry, is very critical in understanding that you can get this hydrogen bonded intermolecularly to something else in this kind of three-centered way. And you'll see this over and over again. And it defines a lot of our biopolymer system. So the book gives a very good description of ion dipole, dipole, dipole. And basically fluctuation, dipole-induced dipole, or London forces. And then it goes through examples, especially with hydrogen bonding, of some very common systems that biological systems that we introduced in chapter 1. So, for example, amino acids. So an amine on one side, an acid on the other. These link head to tail through to form polymers of amino acids. We call those peptides, or if they're found in living organisms, proteins. So these polymers or peptides are proteins, which are polymers of amino acids. And what you find is that because there's a lot of NH hydrogens, that you get a lot of those hydrogen bonding to the acid group, and they can often do it. And this is what helps structure things like alpha helices and beta sheets in peptides and proteins, is this hydrogen bonding network within the molecules. And then it talks about those hydrogen bonding networks in nucleic acids as well, being mainly RNA and DNA systems, and the same type of hydrogen bonding to form these double helices, etc., where it's mainly hydrogen bonding across each of these nucleotides, holding these together. So finally, the book at the end goes through some common mathematics in thermodynamics. And really, this is the mathematics of partial derivatives. And so a partial derivative, you're all familiar with, say, a derivative, so the change in infinitesimal change for this sample in temperature. A partial is given kind of a curved dt, and it means that you're looking at the change in temperature with respect to a specific variable. So it's the partial, typically with respect to some variable, holding all the other variables constant that we're looking at. And really, thermodynamics is about looking at, is basically a fundamental exercise in the mathematics of partial derivatives. And your book gives a mnemonic that Callan and others, and they give the reference to this in the textbook, use this thermodynamic square as a mnemonic to help remember what some of these are. And so I give several lectures on the mathematics of thermodynamics, going through differentials, what it means to be an exact differential, that there's no cross mixed partial are equal to 0, what partial derivatives are, etc. What I want to do here is just quickly remind us what this is showing us. So this is showing us what we just said earlier, that G is a function, and this is assuming a closed system. So we're not looking at any change in the number of moles. So, so this is getting rid of the sum of mu I dni term. So a closed system, and we're just looking at basic mechanical work. So we're just looking at that the change in internal energy is TdS minus PdV. So, and that's saying that U is dependent on S and V. U is dependent on S and V, right? So now we can go around, like we can say that A, which is defined to be U minus TS, so that's flipping, so the change in Helmholtz free energy is minus S dt minus P dV, or A is dependent on T and V. A is dependent on V and T here. G, which we already defined, is dependent on T and P and T. And that's in a sense a double Legendre transform, where you also flip this one, as we showed. And then finally, H, which is defined to be U plus PV. So this will be TdS plus VdP. So H is dependent on S and P, S and P. So in a sense, I've shown you kind of going around this. Now the other thing that's very useful here is to define the partials associated with this. And again, we'll do this later, but just to remind us that it's taking TdP constant S is equal to V dV ds at constant P. And these are known as the Maxwell relations for the partial derivatives of these. The other thing that your book does that's very useful is just to be able to expand a variable. So while the natural variables for internal energy are volume and entropy, say for example, we wanted to expand this instead of entropy, we wanted to do it in temperature and volume space, right? And again, for a closed system. So we can always expand this. So we can take that the total derivative is a sum of the partial, so dt at constant v dt plus du dv at constant t dv. So we can always expand in the number of dependent variables or in any two dependent variables we want for something. And so this is really just going through the mathematics of partial derivatives, especially in the case where you're dealing with exact differentials or ones that don't have mixed partials or equal to 0. Okay. The book does a very nice job of this. There's also numerous, it gives quite a few other references, for example, to Callan's book on thermodynamics and thermostatistics. And there's lots of online resources on Wikipedia and my lecture notes on this as well. And it's one that I would strongly urge. Becoming very comfortable and familiar with the basic mathematics of partial derivatives is critical as another aspect to really learning thermodynamics in this course. So hopefully this gives you an overview of what's covered in Chapter 3. I'll further create videos that give some question and answer of some of the primary questions we're getting this, and then some further delving into screencasts on specific topics within Chapter 3 that students ask questions about. Thank you.